We may remember from our algebra courses that some functions have what are called inverse functions. And an inverse function really just means that if you switch the domain and range, that you still have a function. That's the easiest way of considering it. So if you consider the function, okay, f, which maps elements of a domain to a range or a codomain, the inverse function, which we write as f inverse. This is not f to the negative 1. It's not 1 over f or anything like that. F, it's just a notation. F inverse, that's how you read this, is such that f inverse takes elements from B and maps them to A. Okay, so notice that it's just the reverse. And if it exists, right? So if the inverse relation is a function, then it has an inverse function. We say that that function would therefore be invertible. Okay, in order for f inverse to exist, that is for f to be what we call invertible, it must be the case that to 1. Well, let's take a look at an example of that here. Here we have the function f of 3 equals 2, f of 4 equals negative 1. So let me go ahead and just draw this kind of domain and codomain here, this domain and range. And here I have inputs 3, 4, 6, and 8. 3, 4, 6, and 8. Set B, the outputs are 2, negative 1, 9, and 17. So I might be able to say, and we're kind of speculating here, that the codomain seems to be the set of all integers, and that our range is specifically the elements 2, negative 1, 9, and 17. And so our mappings are pretty clear-cut. 3 maps to 2, 4 maps to negative 1, 6 maps to 9, and 8 maps to 17. So while I can write f of 3 equals 2, f of 4 equals negative 1, etc., notice what would happen if I reverse these. Right? So if I wrote B first, then I wrote A second, and still put the same elements in here, that now what I'm basically saying is, given an output, let's determine what its corresponding input was. In this picture, we're saying, hey, based on the input 3, your output is 2. But here in this picture, based on an output of 2, your input was 3. An output of negative 1, the input was 4. An output of 9, the input was 6. And for 17, it was 8. So if we were encrypting values, encrypting meaning we were trying to code values so that nobody knows what those values were, then somebody who, if let's say you were to encrypt the value 3 into the value 2, you could unencrypt it because the function is 1 to 1, right? Every output has one input as well. And now we could also write the notation like this. We could say we can't say f of 2 equals 3 because that would suggest that an input of 2 gives you an output of 3. But it's actually f inverse of 2 gives you 3. So what was the input that generated an output of 2? It was 3. What was the input that generated an output of negative 1? That was 4. What was the input that generated an output of 9? Well, that was 6. And f inverse of 17 is equal to 8. So we can always, given the output, distinctly determine what the input was, as long as the function is invertible. So here, f inverse exists. And so we would say that f is invertible. That's analogous. And you could also determine that f is 1 to 1. Let's look at another example. Here we do have a function, 2, 3, 4, 6, 9, 3, and 8, 7. Again, I'll just draw sets A and B here for the visual. So we have inputs 2, 4, 9, and 8. And then we have outputs 3, 6, 3, and 7. So just 3, 6, and 7 are distinct. 2 maps to 3, 4 maps to 6. But look at this, 9 maps to 3 as well. 8 maps to 7. So is this a function? Yes, because every input has one output. However, not every output has one distinct input. So for example, I could say that f inverse of 6, well, what was the input that gave me an output of 6? It was 4. If I told you, hey, I got an output of 7, you could tell me that the input was 8. But if I say, hey, my output is 3, what was my input? Well, it's possibly 2, or it was possibly 4. So since we can see that the function is not one-to-one, in other words, there is an output that has 2 inputs leading into it, we do not have an F inverse. F inverse does not exist. We could say F not invertible. Or we could say that F is not one-to-one. Perfect. Now let's look at rather than ordered pairs, let's look at an actual mathematical equation. F of x equals 2x plus 1. Okay, well, we know that we could generate ordered pairs. Okay, and I'm not going to do this type of drawing because there are just infinitely many x's that we could feed into this function. But as an example, and sometimes we write y in place of f of x. If x is 0, we would have an output of 1. If x is 2, we would have an output of 5. If x was -7, we would have an output of -14 plus 1 is -13. And we can kind of generate a bunch of infinitely many ordered pairs. Now, if I can find an inverse, that means that given a y value, I want to be able to determine what was the x. So let me write it like this. Y is equal to 2x plus 1. And again, my objective here is given a y, how do I figure out what the x was? Well, I'd have to plug in a y value. For example, if I plugged in 5 for y, and I said, what was the x that got me that? I could subtract 1. 4 equals 2x, divide by 2, and I get x is equal to 2. And that's exactly what we came up with. So I would be able to say that f inverse of 5 is equal to 2. Now, how do I know this function is invertible? Well, in order to figure out what x is, we have to subtract 1. Minus 1 equals 2x. And to solve for x, I'd have to divide both sides by 2. And so I'm doing the same thing as I'm doing over here, but I'm just doing it symbolically. So x is equal to y minus 1 over 2. The question is, will this always generate just one x? Well, let's think about this. If I give you a number and I subtract 1 from it, then that produces a single value. If I then take that result and divide it by 2, that will still just be one value. So every y value will produce just one x. Rather than writing this as x equals y minus 1, I'm going to write it like this. I'm going to say f inverse of y is equal to y minus 1 over 2, right? Because the f inverse takes a y value, outputs an x value. So x is equal to the f inverse of y, which is equal to y minus 1 over 2. You may have done this before, this weird thing where you switch the x and the y, you put x in place of y and y in place of x, and then solve for y, and then write it as f inverse of x. I think that's a bad practice because it gets confusing as to what x really is. X is our input column, y is our output column. So when we write the f inverse function, we should indicate that its parameter, its input, is actually a y value, as opposed to making this f inverse of x. Consider the function f of x equals x squared plus 4. So therefore, since every y has one x, f inverse exists. Okay, here is that f inverse function. Consider the function f of x equals x squared plus 4. Show this function is not invertible. Okay, well, that boils down to the same process. And you might be able to see already that anytime you're squaring values, it removes the sign. So an x of -1 and an x of +1 are going to generate the same x squared. But just to show that this is not going to be 1-to-1. In fact, it's a parabola that's shifted up 4 units. And so every input will have just one output. But if you look at one output, for most outputs, you're going to have 2 inputs, that one and that one. that one, and that one. So while it passes the vertical line test, it wouldn't pass a horizontal line test, which would indicate that for a given output, is there only one input? Okay, so here we go. Subtract 4, you get x squared. Now, how do you solve for x? Well, you take the square root of both sides. But remember, when we take the square root of something, we have to realize that this could be a positive or a negative value. Right, so let me give you another example. X squared equals 9. We know that x can be plus or minus 3. Well, it's going to be plus or minus the square root of 9, which is equal to plus or minus 3. Great, so here we have x is plus or minus the square root of y minus 4. Okay, well that's two values, right? That leads to value number 1, which would be the positive square root of y minus 4, and value 2, which would give me minus the square root of y minus 4. So this gives me two outputs, and therefore the function is not invertible. So we have a very distinct way to determine whether inverses exist. Again, this is really valuable stuff whenever we're considering things like encryption, where you send somebody an encrypted message. In order for them to be able to decrypt it and get a unique output, that means that the F inverse function has to exist. That means your relations between inputs and outputs has to be 1-to-1.